Happy Thursday. We are almost there. You do get to play Are You Smarter Than a Harvard Graduate again today. And this one, if experience serves, some of you will be. None of you will be dumber. Caleb?
Is the reason we do brain teasers every Monday and Wednesday so that we can think more outside the box in the sense of like these videos as well?
Yeah, I told you that, right? That scientists need to be able to think laterally and think outside the box, and I'm building that skill. It's the only way I know how to really build that skill. Yes, and we only do them Mondays and Wednesdays because this is school and we can't have too much fun. You will get the occasional bone thrown to you on Fridays. Yep, yep. Okay, so let's see. To review the most important thing from yesterday, we did talk about chemosynthesis. Chemosynthesis and what was the other thing? I don't even remember. But the really important thing was ecological succession, this set of steps that is fairly predictable in two different kind of flavors. There's the kind where there has been nothing, no soil, and it's just starting on bare rock. That's primary succession. And then secondary succession is what happens around here when a field gets cleared or there's a forest fire and stuff starts to regrow in that soil. The first things to move in that actually, if you would add this, I don't know that you know how to spell lichens, so I went ahead and put it in there. I can't remember if I did that yesterday or not. So the pioneer species we did say were weed type plants in secondary succession, but in primary succession, lichens are almost always the first ones. Really, we've mostly just been talking about the living part of ecology, the biotic factors, right? And so it's time to move into some of the more important abiotic factors. To connect it back to your initial inquiry activity with the slides and the consequences, ooh, that's a good picture of secondary succession. I forgot to show you. Kind of over time, we get the annual plants and the grasses, and then the shrubs and trees, and then like sort of what we call the climax community of hardwood trees. The climate question, again, don't write this down, is one of your initial scenarios. The idea that the climate is getting warmer and the effect is more pronounced at the North and South poles, which is true. But what's climate anyway is going to be our first question. What is climate? Like, what's the climate out right now? Cold, chilly? That's not climate. Good. Good. What is that? That's weather, and weather and climate are different. How is climate different from weather? Climate is long-term averages over time. Exactly right. The long-term average conditions in an area. Now, the first thing you need to know about our climate here on Earth is that we are very lucky. One planet in from us, which is what? What's the second planet from the sun? Venus, right. Go there and get out of your spaceship and your face melts. It's super duper duper stiflingly hot on Venus. One planet away from the sun, super duper cold. What do we have that they don't have? Why are we so comfy? Because we are super comfy. Caleb? It is our atmosphere. It's not that Venus doesn't have one. Venus has a super duper thick one with lots and lots of one particular greenhouse gas, which is water vapor, that basically traps heat from the sun under that blanket of atmosphere and keeps it just fryingly, I guess steamingly hot there because of all the water. Mars has almost no atmosphere, and so no heat gets trapped. We have this lovely blanket of just the right gases to create just the right, what we call greenhouse effect. The greenhouse effect works because sunlight, you know about wavelength of energy, about how there's short wavelengths and long wavelengths. Well, the visible light spectrum and non-visible stuff of sunlight is pretty short wave stuff. And it turns out that short wave radiation gets through things better, at least the things we're talking about, than long wavelength energy. It's very much like, okay, picture yourself in the summer at the grocery store with your parents. You go in and you forget to crack your windows on your car, and your car has a dark interior, and you shop for, say, a half an hour. You come back out, and you open your car door. What happens? Just this wave of heat hits you in the face, right? Like super hot, like low oven temps. And that's because the same thing is happening. The short wavelength sunlight is getting through your car window, no problem. And then it hits the seats. And the seats are dark colored. So is the earth, by the way, mostly. And so what happens to that energy that's in that short wavelength sunlight when it hits the dark seats? What happens to it? Abby, what happens to it? I saw your eyes drooping. It gets absorbed, and then what? What happens when short wavelength light hits a solid dark object is it absorbs that heat and then absorbs that energy, and then what?
Not like reflect, but like pushes it back out to make the car hotter.
There is actually reflection going on too. And when we're talking about the Earth or a car with a white interior, you know, the white parts of the Earth, like the frozen ones, they do reflect a lot of that light right back out into space. But the stuff that gets absorbed then does what? It gets turned into heat. Short wavelength light gets turned into long wavelength heat. And that's what you see happening here in this diagram. And that heat is not nearly as able to get through the atmosphere or your car window. Your car window blocks almost all of the heat. Glass is a very good insulator. The Earth's atmosphere has CO2 and water vapor and methane in it. And when long wavelength heat hits those molecules, it transmits that heat and gets trapped. And the heat kind of gets reflected off of it and back down. And just enough of that heat gets trapped under the atmosphere to keep us nice and comfy. So that's kind of in a nutshell how the greenhouse effect works. To write it out, atmospheric gases, and those are the big three, carbon dioxide, methane, and water vapor, act as the car window. The sunlight gets in, gets converted to heat, and the window keeps that heat below the atmosphere. All right, so this is actually a two-part question. Both have to do with climate. The first question I want you to answer in as great a detail as you can is, I'll get my prop out for this. Hello, not the wig. We can all agree that it's warmer here at the belt of the planet we call the equator than it is here and here, the north and south polar regions, yeah? Okay, simple question. How come? Why is it hotter at the equator than it is at the poles? That's question one of two. Go ahead and write your answer down now. Okay, looks like most folks are done. I've seen several partially correct answers, which is awesome. That your earth science education has at least been decent so far. Here's the related question, and some of you are going to realize that it's the question you were actually answering on the first part. But the second question is this: okay, it's hotter here than it is here, but how come here and here, like where we are, How come we have seasons? In other words, why is it hot in the summer and cold in the winter?
Misconceptions that they had on entering grade school to test how a lifetime of education affects our understanding of science. We asked these recent graduates some simple questions in astronomy. Consider, for example, that the causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happen because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and then hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun, and it gets hotter when we get closer to the sun, and it gets colder when we get farther away from the sun.
These graduates, like many of us, think of the Earth's orbit as a highly exaggerated.
Raise your hand if you said something like that for what causes the seasons. So many people think that, and that could not be farther from the truth. It turns out that that is not true at all. In fact, the Earth's orbit is almost a perfect circle. It's very slightly elliptical, not enough to produce any distance variations. But to understand why the seasons actually happen, you have to understand the answer to the first question I asked, which I think a couple people got partly right. Like AJ said something that rang true about why the equator is hotter than the poles. What did you say, AJ?
So the sun hits the equator more directly.
The sun hits the equator more directly than it hits the poles. This has nothing to do with what a lot of you said, which was that the equator is closer to the sun than the poles are. It's true that the equator is closer to the sun than the poles are, but that's like 1/1000th of the total distance between the Earth and the sun. It produces no temperature variation, right? It's not hotter here than here because this is, a couple thousand miles farther away from the sun. We're talking about millions of miles, right? So why? What is it about the Earth that makes the sun hit more directly here than here? Because when you say directly, what are you talking about? What is the what of the sunlight? The what?
The rays.
Okay, but like the what of those rays as they hit the Earth? What changes when we say direct versus indirect? We're talking about, what did you mean?
So like, you were like pointing at us, it'd be more of like a glancing glow, but if it's at the equator, it's coming.
When he does that, when he says it's like this, but at the poles it'd be more of like this, like a glancing blow. What's he changing about the rays of the sun? The angle, exactly. Why is the sun hitting at a more direct angle here than here?
The tilt of Earth's axis.
You guys are programmed to say tilt. They've hammered tilt into you. Tilt is the answer to the second question. What's the answer to the first question? Why does the sun look? Got this. Direct, indirect. Direct, indirect. Why?
There's not much more place for it to bounce off. If there's no space on the outside.
Direct, indirect. Direct, indirect. Why does the sunlight get more spread out here than it does here? What is it about the Earth? This is so hard, and it's so easy once you say it. Because the Earth is round. Yes. When sunlight hits a ball, when a flashlight hits a globe, when a laser pointer hits a globe, if we keep the rays parallel, it's going to hit directly in the middle, and as you get up to the top, it's going to hit that glancing blow that AJ said. Can we agree that this laser pointer is transmitting more energy per square inch now than now. It's the same amount of total energy, but it's being spread over more square feet, square miles at the top than it is in the middle. So there's less heat being transmitted. The Earth is unequally heated by the sun because it's round. Are we there? Okay. Let's see what else she has to say. I can't remember if it's important or not.
Ellipse. Even though the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons, we carry with us the strong, incorrect belief that changing distance is responsible for the seasons.
I took physics, planetary motion, and relativity and electromagnetism waves.
I've never really had a scientific background whatsoever, and I got through school without having it.
That dude took physics. All right. So let's talk about that briefly. We call those latitude effects. And latitude effects happen because the Earth is round, which makes the incoming photons from the sun transfer more heat per square mile of Earth at the equator, and progressively less as we get further and further away. Because the amount of heat transfer depends on the angle. And the angle changes because, of course, you are shooting these rays of sunlight at a ball. So again, the answer to that question is not the tilt. It has nothing to do with the tilt. It's the roundness of the Earth that changes the angle of sunlight that it hits at different latitudes. But then we have to think about the fact that the Earth is going around the sun, staying mostly the same distance from the sun. But what's changing? As this thing, if I'm the sun, goes around me and comes around the back. If I'm the sun, what am I looking at most directly right now? Kazakhstan, but let's see. How about now? What am I looking at most directly? Yeah, this is July, right? This when I'm the sun and I'm looking at the top half of the Earth more directly than the bottom half, that is summer for the northern hemisphere, winter for the southern hemisphere. So this is the one, the seasonal question is the one that the answer is, well, the tilt of the Earth on its axis as the Earth goes around the sun basically slants the Earth top half towards the sun, bottom half away from the sun part of the year, and vice versa the other part of the year. And that, I think, once you get the first answer, the second answer really starts to make sense. So those seasonal effects. Sorry, more to write about latitude effects. So the angle of heating is what it's all about, and the Earth's tilt and its position in its orbit around the sun is what causes seasonal changes. Okay, we can write that out all we want. Pictures are better. Let's draw a picture. Don't draw yet. I'm going to show you a couple of different versions. I'll let you guys. All right. Don't draw yet. But we have lines that we draw on the Earth. Of course, the equator, where the most direct sun hits. The tropics, which is why we call it the tropics, right, are between the Tropic of Cancer, which is 23.5 degrees north latitude, and the Tropic of Capricorn, 3.5 degrees south. So between those two, we call the tropical climate zone. There's 3 climate zones. Then we draw 2 more lines. The Arctic Circle, which is 66.5 degrees north, and the Antarctic Circle, 66.5 degrees south. And above and below those, we call polar zones, like the poles of the Earth. And then between the two, where we live, what do we call that zone? What do we call that zone? The temperate zone, that's us. We get seasons. By the way, do you know what Arctic and Antarctic actually mean? Those words? It's so dumb. It's Greek. Arctos is bear. So bears, no bears. Is literally what that means. And it's true, right? There's polar bears, they live in the north. No bears down there. Correct. Penguins live in the Antarctic regions. And further north, southern tip of Africa has some weird penguins. But yeah, they don't get all the way north. Okay, so that's true like 2 days a year, right? Like the equinox. But every other time of year, it's some degree of either this, right, where it's not very direct sun in the northern hemisphere for us and it's winter, or this, where it's very direct sun in the temperate zone of the northern hemisphere and it's summer for us. Which one do you want to draw? Summer or winter for us? Summer? Yeah, okay, so draw that. We're almost there. We've got to talk about weather tomorrow. We'll talk about biomes very briefly on Monday. We'll review Tuesday, and we're looking at a test on Wednesday, chapter 3 and 4 tests on Wednesday. The first real full-length test. That'd be awesome.